recording. Slight modification with that is we could say we get a mix of phases. So if we mix two liquids and we saw a gas, well, we started with liquids and we got the gas. So there's a mix of both liquids and gases. So that was a chemical reaction. Okay, again, it just gets that kind of weird gray area. Yes?
One of the questions in the book,
Mm-hmm.
number one actually, is which of the following is evidence for a chemical reaction?
Yep.
A, heating copper in air produces a black solid.
Yep.
B, heating copper in a vacuum gives a brown film. I answered both were chemical reactions, where actually A is and B is a physical change.
So the issues with that is going to come, again, from knowing what's happening within each of those. Any film that you're putting on that is a permanent color change. So in both those cases, based on the way we've discussed this, we would say those are both chemical changes. The reason why putting into a vacuum is not a chemical change is what did you react? In a vacuum, all you have is the copper metal. And the other thing is heat. There's nothing to chemically react. Why are you getting that brown film?
Oxygen?
To generate the black film in the first one, yes, it's going to require oxygen. So when they heat up copper in air, it's reacting with both the materials coming from the flame and oxygen in the air.
Okay.
And you're generating a copper oxide film.
Okay.
When you're getting that weird brown thing in that, what exactly is happening there? You could probably make a pretty solid argument that you are getting a chemical reaction.
I would think.
How do you make that decision? That's where I have an issue with trying to describe these chemical reactions. Okay? So try your best attempt with each of these. Realize that the ones I'll give you will try and be very black and white. They'll go over examples that we talked about. Okay? Like we talked about sugar dissolving in water. Chemical or physical? That was a physical change. Those sugar molecules didn't change their structure. They're now separated into the water. But when we dissolve salt into water, we call that one chemical. Why? We don't have sodium chloride anymore. We have sodium ions and chloride ions. How do you know that? Well, ultimately, you'd have to have enough experience with the chemistry to know that that's what's going on. Okay? Where do you get that experience? Ultimately, you see those reactions or you're told those reactions. So I've now told you. So those would be fair examples to pull at for any kind of quiz or test. A lot of these physical chemical reactions, you're just going to have to kind of go on a case-by-case basis to evaluate, which is unfortunate, but that's the level that we have to work at under these presumptions. That's all we really have. Okay? So our physical changes, forming a gas, so we mix two liquids and we see a gas. If we mix two liquids and we see a solid form, that's a precipitate, also a symbol for a chemical reaction. So in this case, we see that yellow solid come out of that solution. We could look for a permanent color change. Even with the permanent color change, we don't get a clear definition on what makes it physical or chemical. Because we could get a permanent color change by mixing blue and red food color. Is that a chemical reaction? No, all we've done was mixed two dyes, the dye colors, then interact with our eyes differently. We now have a permanent color change because it is purple. There's nothing we're going to do about that. But it's not a chemical change. Okay? So with rules 1, 2, and 3, we can get all sorts of examples and counterexamples to make those rules effectively useless. Okay? So you have to be careful with how you apply those definitions, and you're just going to have to do it on a case-by-case basis and kind of weed your way through it. Okay? The one that works, at least as far as I can tell, exclusively as a rule is a change in energy. Okay? If our reaction gets hot after mixing two liquids, that was a loss of energy. That's why our reaction got hot, is we can feel the heat coming into our hand. That energy had to come from somewhere. That somewhere was the chemical bonds either breaking or making. Okay? Same idea with an absorption of heat. If it gets colder, That's either chemical bonds breaking or making. Okay? So a change in energy is always going to be a big tip-off that you're looking at a chemical reaction. The other ones can be kind of gray areas. We can come up with odd cases in each position. Okay? Big characteristics for that. If we throw any one of our alkali metals into water, we can get this big exothermic reaction. Releases a lot of heat, also releases light, and light, as we said already, was a form of energy. Okay? Questions about our chemical and physicals? Okay. So if we look at a chemical reaction, we picked this chemical reaction because it forms hydrogen gas at the end. Okay? So what you're responsible for in this class is a lot of the individual pieces with an individual chemical reaction. So the first thing that you're going to have to be able to do is take that individual formula and turn it into a name. So if we were going to write out in words what that reaction says, is that we would have solid sodium hydride. How do we know it was solid? The S after it. Solid sodium hydride reacts with or is mixed with acetic acid. Why did I call it acetic acid and not hydrogen acetate? The AQ and there's a hydrogen, which means it's an acid. So by saying acid, we can imply both the hydrogen and the fact that it's aqueous. So we got solid sodium hydride reacting with acetic acid to form sodium acetate, aqueous sodium acetate, and hydrogen gas. So what we've done is converted all of those individual symbols into neat little words. Okay? The most important aspect of that is that when we talk about that last one, we said hydrogen gas. How do we know it's a gas? It says G. If I just referred to hydrogen in general, what phase would you associate with hydrogen?
Gas.
Why gas? In its natural state, it's a gas. Okay? So we'd have to do some weird stuff to get it out of the gas phase. Okay? Either as a liquid or a solid. So our gut response is going to be to make it a gas. The next issue, why is it H2 and not just H? Some elements, when they show up in their elemental state, are diatomic. Okay? Thankfully, it's not a lot of them. There's only 7 of them. You need to know that these elements are diatomic and that when you use them in a balanced equation, if you make or consume any of these elements, you have to make sure that when you write it down, they are diatomic. Okay? You have to specify that. So that's part of the balancing of the formula of hydrogen gas. Okay? What are those 7? We're looking at hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. For me, personally, I happen to remember the have no fear of ice-cold beer because the first letter matches the first letter of each of the elements. And it's only the first letter. Okay? This morning, people didn't like cold. There's a little cold, looks like carbon. Yeah, it's not perfect, but that's the best I could come up with or remember. They tried to come up with their own. For some reason, I'm going to share with you guys, they came up with clear bros was one suggestion to get okay. Have no fear of ice clear bros. I don't know what a bro, how that applies. But the other one that came out was bras. Bras makes a little bit more sense. But ultimately, you just need to remember those 7 elements, however you want to go through and do that. Okay? The other method that I would use is that we've got hydrogen as kind of your exception, and then the number 7 hidden with the other ones. Okay? Your question?
I'm good.
Okay. Any other questions with this? Okay, let's go ahead and take a look back at our chemical reaction because we didn't do any real balancing last week or Tuesday. We now need to go through and make sure that our equation is balanced. As we learned back in chapter 1, one of those earlier chapters, we have conservation of mass and ultimately conservation of energy. which means in the process of running a reaction, I cannot create or destroy matter. We're taking this a step further and making it a little bit easier on you. We can't create or destroy atoms, okay, or individual elements. It's not officially true. We can tweak that, but we'll do that at some other point. So if I start with a sodium atom as a reactant, what do I need to end up with in the product? I need that sodium atom to show up in the product. So to go through and balance, what we're going to go through and do is identify all of the individual elements. So I have sodium. On the reactant side, how many do I have? 1. Now we'll look to the product side. How many do we have on the product side? 1. So far, our sodium's balanced. We can move to the next thing. Okay, what next thing do we want to do? Okay. How many hydrogens do we have on the reactant side? 3, 4, 5. Okay. Product side? 2 and 3, 5. So our hydrogens are balanced. What's the next thing we could balance? Okay, I heard oxygen. I also heard sodium. We already balanced sodium. We can come back to carbon since you're now listing it. We can write that down. How many oxygens are there on the reactant side? We've got just 2 oxygens. On the product side? 2. Carbons? This involves lots of coloring. And, oh, that was horribly drawn. And 2. What does that mean? Everything's balanced. Okay? So first question that we could ask with this, as far as a multiple choice question would be, is what is the sum of the coefficients of the balanced equation? What are the coefficients? The coefficients is the number in front of every single one of these. So if I ask for the sum of the coefficients, what's my answer?
4.
4. How'd you get 4? I don't see any numbers there to add.
Because you're going to assume 1.
Why do we assume 1? We wouldn't write anything at all if it was less than 1. Okay? So just by the sheer fact of writing H2 gas or sodium acetate aqueous, we are implying that there is 1 there. Okay? So the sum of our coefficients in this case would be 4. This method is going by atom. There are other methods to balancing, and we'll take a look at that one other method here. What's the other option? So I'm going to erase all this. You cool with me erasing? Okay. What's the one other way we could go through and balance? Instead of balancing atoms, I could go through and look for pieces that don't change, which is effectively what we did with the atoms. We went through and looked at sodium as an atom, and we compared across. And it was 1 and 1, right? What was the next thing that we went through and did? Hydrogen. Okay. So I'm going to take a break away from hydrogen, okay, and say I don't want to balance hydrogen right away. And we're going to look at sort of a reason why we don't want to balance hydrogen to start things off. So the next thing we went through and balanced was our oxygen and our carbon. Before we even do that, let's take a look at this piece right there. What is that piece? It's our acetate ion. What is this piece right here? Acetate. Did it change? No. So I could go through and balance the carbons and oxygens independent as individual atoms, or instead I could go through and say, actually, I'm going to balance the complex ion. I'm balancing that entire piece. How many of those pieces do I have on the reactant side? 1. How many of those pieces do I have on the product side? I left off the 1 on the hydrogen. Okay. Not a super big deal for balancing in this case, but more complex ones it becomes important. So the last thing that we would have to balance would be our hydrogen. How many hydrogens on our reactant side? I'm actually hearing a lot of the correct answer, which is good. The answer is 2. Why is it not 5? You've already accounted for that H3 in the middle when we looked at the acetate ion, so we won't count it a second time. Okay? So this is how your polyatomic ion method can get you into trouble, because you go through and you double count atoms that showed up in multiple places. Okay? So it can be problematic, but it can be time-saving. You get to decide which method works best for you, either doing it by atoms or by doing it by polyatomic ions. Okay? I'll tell you, as far as I'm concerned, I'm going to do the ions for an example later on, okay? Because otherwise it becomes a real pain. How many hydrogens do we have on our product side? 2. We're looking at the unaccounted for atoms. Okay? This could be, for balancing, it could be a really great thing to have different colors. Why? Once we've circled our atom with that color, we now know that we can't count it again because it's already been counted. Okay? Questions about balancing? Okay. And yes, this was a really easy example. We will see more difficult ones. Okay?
So they will always be balanced?
They will not always be balanced. You have to balance them. Okay? Sometimes I'll say balance this equation and then be kind of a jerk because it will already be balanced. So you'll go through and attempt to balance it and be like, well, crap, it's already balanced. Okay? Why did you tell me to balance it? Because you should know that it's balanced. Okay? Questions about any of that? What happens? So if we look at an equation for sodium chloride, solid, dissolved in water, it becomes sodium ion and chloride ion, aqueous. If we looked at sugar, anybody know the formula for sugar? Good. C6H6O6. I am making it up, actually. What we get is C6H6O6 aqueous. Molecule stays the same. How would you know that? I told you that's how you knew that. That's the only reason you would know that. Okay? D, what's going on with D? We're seeing a temperature change. Temperature change when we mix two liquids. That's our fourth rule, if we will, for chemical changes. Number 2. Answer for 2. Answer for number 2.
Oh, B. C.
C.
Why not?
And D.
Why not O? Or I mean B.
Take a look at magnesium. Magnesium is not diatomic.
I suck at
I wouldn't go that far. That's a bit extreme. Magnesium is a solid. How do you know it's a solid in its elemental state? You look at the periodic table, it's black. Black means solid. This says liquid, not in its elemental state. Oxygen, elemental state for oxygen. Gas, this says solid. It is correct in having O2, but it's in the incorrect phase. Both bromine and nitrogen look weird. Nitrogen's a gas. Well, it is a gas. Nitrogen's also one of the diatomic molecules. It has to be N2. Bromine, again, diatomic, has to be 2. How do we know it's a liquid? Again, our periodic table. It's colored blue, which means it's a liquid. Last one, hydrogen. Why is that not its elemental state? Hydrogen is diatomic. It needs to be H2 to be its elemental state. Okay? So, now you get an idea on how we can get those questions out there. The last one, provide a complete balanced equation for the reaction. Elemental sodium reacts with elemental chlorine to make aqueous sodium chloride. Since we just went through and balanced this equation, we're not going to balance this again, so let me cross this one out temporarily. That's now crossed out. What we're going to do is do the answer for that previous one. Started with elemental sodium. What is elemental sodium? Step further. It is Na solid. Must specify the phase. Plus chlorine. Yes, it's a gas, but it's diatomic. Must be Cl2. Goes to produce said sodium chloride, NaCl. What's the charge on sodium? +1. Charge on chloride? -1. Our formula is correct. We're going to address this formula issue in just a second. That's why I gave you an easier example with the sodium chloride. What phase was it? We said it was aqueous. How do we know it was aqueous? Because that's what the question said. The last part of this, it said balanced equation. Is our equation balanced? If we look sodium to sodium, that's 1 to 1. Is the chlorine 1 to 1? No, it's 2 to 1. What do we have to do? We need a 2. We put the 2 out in front. The problem with that, how many sodiums do we now have on our product side? 2. So what do we have to do? Back to our reactant side, put a 2. Okay? So, we are now going to continue to look at balancing chemical reactions. You've now had to push through, in theory, two now relatively simple ones. The first one, we didn't really have to do any changing of those numbers. The second one became more difficult because we actually had to put in numbers for it. Okay? How would you know all of these rules? You read ahead in the slides, and the slides give you the guidelines for balancing equations. Okay? Before we look at those guidelines, let's take a step back here. To balance, what we end up doing is placing whole number coefficients in front of our substances. Why do we never put them as subscripts when we balance our equations? What do the subscripts tell you? The number of atoms in that molecule. If you change the subscript, do you have that same molecule anymore? No. You now change that molecule to a different species. We can't do that. The only thing that, once we're starting balancing equations, is we can put more of that type of molecule, but we cannot change the molecule itself. Okay? And it's easy to get these steps mixed up. So let's go through them and again address what we've got to be careful of. Number 1, okay, which we haven't seen quite yet, but we will in a little bit, predict the products. This is only if necessary. Okay? You may be given what the products are, so you don't have to worry about it. This can be done by classifying the type of reaction. Maybe you're told the type of reaction. If you have that information, you should be able to predict what those products are. Okay? And again, we'll look at examples of that in a little bit. Once you've got your products, you then need to balance the formulas of your products and your reactants. What do I mean? Well, if I gave you potassium sulfate dissolved in water, okay, give me, let's not go there. Let's do this. I want potassium sulfate dissolved in water. So I'm going to give you the reaction. We'll even go through and tell you that you start with a solid. Okay, and I'll tell you that when we dissolve it in water, we get 2 species that are dissolved. We get these AQs. What is the formula for potassium sulfate? What is the symbol for potassium? What is the symbol for sulfate? The gut response of most people, particularly with the format we got set up, is say, okay, well, dissolves in water, we get SO4. What's the charge on SO4? Sulfate's one of the ones I've told you to memorize. -2 charge. Okay, and we'll come up with a reason here why it's really important to have that memorized. And potassium ion. If we look at this, that looks balanced. Unfortunately, it's not. What's the problem with this? Before you balance a form or an equation, you must balance the formulas. Sulfate is fine, potassium ion is fine. There's something wrong with potassium sulfate. What's that issue? Every compound you work with must be neutral. Can potassium sulfate possibly be neutral? No. Why not? Charge on potassium is +1, sulfate is -2. which means when we take the name potassium sulfate and write it out into the formula, we must balance the formula first. To balance it, it is K2SO4. But wait, I said you couldn't bring numbers in as subscripts, right? I said you couldn't do that when you're balancing the equation. What are we balancing? The molecule, the formula. The formula, you must use subscripts. We need 2 potassium ions to balance out the sulfate. Now that we've got the formula balanced, now we can balance the whole equation, and we'd have to put a 2 over here. Why does the 2 go out in front and not as a subscript? Because if we make it a subscript, it's not potassium ion anymore. It would be dipotassium ion, which we don't have. Okay? Questions on that? Okay. We will see lots of examples. Whoa, that was way further than I wanted. Once we've got our formulas balanced, now we can begin to balance the overall equation. You can use any atom you want, particularly for this class. I would recommend that you do not start with hydrogen or oxygen. Okay? The only reason being is that if you have to move into further chemistry classes, particularly 152, you want to balance all atoms before hydrogen and oxygen. Then you balance hydrogen, then you balance oxygen. And the reason they get shifted out there is because when we move into a particular type of reaction for, say, batteries, we have to balance the hydrogen and oxygen in a very odd fashion, in a fashion that actually takes students that already know how to balance equations a full lecture to understand. Okay? So we're going to avoid that issue altogether. You just need to balance all of your atoms. Okay? Remember, there is a simplification. We could balance atoms. We could also balance the polyatomic ions. Okay? We can group those as their own unit. Okay? Once you've got that, or started to do that, you'll place whole numbers in front of formulas to increase the amount of the atoms that follow it. Remember that that coefficient applies to every atom that follows it up to a mathematical operation. Once you hit the operation, we clear effectively that multiplier, and we can start up a new multiplier. Okay? You will then repeat steps 3 and 4 for all of your atoms or polyatomic ions until you've done them all. Once you have done them all, because you've potentially now changed the numbers of those atoms by putting in different numbers throughout your equation, you need to check your work. So you go back to your very first atom, and you check to make sure it's balanced. Then you do the next atom and make sure it's balanced, and the next atom. Okay? If you changed any numbers, what do? You repeat steps 3 through 4 again. Okay? At that point, if you haven't changed any numbers, that's pretty cool. We might say, that's good, you can stop. I'm going to challenge that and say, no, you cannot stop. Check it again. Okay? At that point, is it okay to stop? No. Check it again. Okay? By the time you've gone through and checked this, you should have checked it so many times that you want to punch somebody. Okay? Just don't punch me or anybody else. Okay? But you should be checking this so many times that when you get to the point of saying you're done with balancing, there is no reason for you to check your answer. Why? You've already checked it. You are now 100% certain you are correct. Only once you are 100% certain you are correct may you check your answer. Okay? Which seems kind of counterintuitive. Well, if I already knew it was right, why would I check my answer? Good call. That's true. You shouldn't be checking your answer. You should know it was right before you went and looked. Okay? If for any reason you get stuck in the process of balancing, what should you do? Starting over is a good option, but if you don't know where to start, what should you do? I've seen lots of students do this already. Oh, I have no idea where to start. What's the answer? Good call. On the exam, whenever you look at the exam question and you decide, oh, I don't know how to do this, can you look at the answer? No. You're doing yourself a disservice by looking up the answer. What should you do instead? How do you figure it out, though? That's the challenge. Are there, say, sources of information that explain how to balance? Say, like the PowerPoint slides, or Google, or the lecture video that's been recorded and posted, or your textbook. You have these references. By going through that extra step and forcing yourself to look up how to solve it, you will actually remember how to solve it because you had to work for it. Okay? If you don't have to work for it by looking at the answer, you will get it wrong, okay, when it comes to the test because you haven't built that memory muscle up. Okay? Very, very, very last step that you've got to watch out for. If you did everything appropriately, step 7 should be irrelevant, but it's a good check. Verify that you use the smallest whole numbers possible to balance. Okay? Very rarely happens or pops up where you have to watch out for that. We'll look at an example here in just a second. Okay? Questions about any of those steps? Okay? What's the awesome part about balancing equations, personally, in my opinion? Step 5. Step 6. Why is step 6 so cool? By the time you finish balancing, you know the answer. You're right. That's it. Okay? Or you go through and you've checked your work and it doesn't match up. You know you're wrong. Okay? There is no gray area between this. You either checked everything and it adds up, or you didn't check everything and it doesn't add up and you're wrong. Okay? So balancing can be really, really nice as far as a question goes because you can guarantee yourself the right answer. The only time it becomes a problem is if you answer the wrong question. Okay? So we'll take a look at a couple examples here. Yeah.
Something that I've done that I think has been really helpful is I come to the library to do my homework,
Mm-hmm.
and then if I don't know the answer or if I double check the answer and it's wrong, I go to the answers in the back of the book. Then,
Everybody does. I did it too.
I go to the lab, and, the tutor, and I
Mhm.
say, okay, here's the answer. How did they get that?
Yep.
And,
So yeah, ultimately, if you can't find the answer anywhere else, you have to find somebody else that knows the answer and knows how to get that answer. Okay? I'm on campus, physically on this campus, 45 to 50 hours a week. Okay? That doesn't count the time that I'm spending at home working on new problems, building exams, or anything else. So I can be found here. At this point, I've had 3 out of 100 students regularly see me in office hours. Okay? Yes, there are schedule conflicts. That's awesome. Also in the syllabus, it says by appointment. How many have asked for an appointment? Okay? If you aren't making the effort to get that help from me, you have to make that effort to get the help from somebody else. Okay? And that's fine. I don't know everything. Somebody else can potentially teach it better. So go to them to get that help as well. Okay? You might not like me too. I smell funny sometimes. Okay? So let's take a look at some problems. You'll notice that there is a slight tweak to these from what's posted online. I just did a last second adjustment. I wanted to do a different problem on it. So let's balance that first equation. Okay? So we would start with hydrogen's a good place to start. Why did you pick hydrogen? 2 really good answers, in my opinion. It's first, good first answer. It's the first one we encounter, and
it looks balanced on both sides of the equation.
I wouldn't even go with that. That's just because this equation is simple. We go back to the rules. What was our rule? Okay, begin to balance the equation starting with any atom other than hydrogen and oxygen. Okay, what I briefly added after that was start with hydrogen, then do oxygen. So what should we start with? We don't have any other atoms, so start with hydrogen. Okay, so hydrogen. How many hydrogens do we have on the left-hand side? How many hydrogens do we have on the right-hand side? 2. Awesome. What does that mean? Hydrogen is balanced. Take a look at oxygen. How many oxygens do we have on the left-hand side? How many oxygens do we have on the right-hand side? 1. So here's a good case where we could adjust with this formula issue. A lot of people would say, okay, I need 2 oxygens. Right? Yeah, now we have 2 oxygens. Did we actually make what the equation originally asked us to make? No. Instead of making water, we've now made hydrogen peroxide. That's a pretty big difference. Drinking water isn't really going to hurt you. Drinking hydrogen peroxide is really not a good idea. Okay? So how do we balance it? We need to put a 2 as a coefficient in front. That 2 now applies to everything after it, including that oxygen. So our oxygen is now how many on the right-hand side? 2. I think I heard a 4. Okay, no, you're going to get to that 4 in just a second. Okay. We've now gone through and balanced. What did our rules then say to do? Check again. Go back to hydrogen. How many hydrogens are on the left-hand side? 2. How many hydrogens are on the right-hand side?
4.
We have the 2 and the 2 again. We have 4 hydrogens. So that doesn't balance. So how do we fix that? We'll go back over to our left-hand side and put a 2 there. Now the 2's both apply, and we get 4. Check our oxygens. Oxygen on the left-hand side. 2. Oxygen on the right-hand side. What's our next step? Do it again. Okay. Hydrogen. How many hydrogens do we have on the left-hand side? Right-hand side. Oxygens. And what's our next step?
Do it again.
Thank you. Do it again. Okay. Are we correct? Are you tired of me asking you to do it again? No? Okay, do it again. How many hydrogens are there? 4. How many oxygens? 2. Okay. Tedious, obnoxious, I know. Deal with it. Okay, get the answer right. We'll all be happy. Okay. Questions about that first one? Question on the exam. What is the sum of the coefficients for the balanced equation? So let me clean some of that up a little bit. And we'll just erase all of that because that was all of our work. Sum of the coefficients. Answer choices. 1, 2, 4, 5. What's your answer? What's something that's obnoxious about all of those answers? All of those numbers have the potential to be right. Okay, we could make it even more obnoxious, actually. Why not? You all think I'm obnoxious, right? You don't have to answer that. And 5. Sum of the coefficients is D, 5. E. I changed my numbers, that's why I got confused. Thank you for correcting me. E, 5. 2 plus 1, where's the 1 coming from? There's an implied 1 in front of that oxygen. 2 plus 1 is 3 plus another 2, 5. So 5 is a good answer. What's the coefficient in front of hydrogen gas? 2, or B. What's the sum of the coefficients for the reactants? C, or 3. What's the coefficient for oxygen? 1. Why do I have 4 up there? 4 is a legit mistake answer, because you did not count the 1 in front of the oxygen. So all of these answers have the potential to be correct. How do you know which one's the correct answer? You read the question. Okay? If the question asks for the sum of the coefficients for the entire reaction, what should you do? Add them all up. If it only asks for one of them, answer just for that one. How can you ensure that you're answering the question correctly? You could read it again, but more than likely you'll read it again wrong. I'm not saying it's your fault, it's just the way it's going to happen. When you read the question, underline, circle, star where it's asking, what it's asking for. Interpret it so that you know that you're answering that question. Okay? That way, worst case, when you get back to your exam and you go, I thought I answered it right, you can go back and say, well, this is what it said to ask. And you look at it and go, oh, actually, I read the question wrong. Okay? Perfectly valid. What we're trying to do is build up test-taking techniques as well as understanding the material. Okay? So when it comes to the exam, what should be written on your multiple choice section? A whole bunch of stuff. It never ceases to amaze me how empty the multiple choice section of an exam is for any student. Okay? Write that information down. Do some interpretation. Biggest reason why? There was one correct answer for this question. How many wrong answers were there? 4. If your test is 60 questions long, okay, by the end of the test, you've seen 60 correct answers and 6 times 4, 240 wrong answers. If you're now going to guess, what answer you're probably going to guess? The wrong answer. Your brain is shot at the end of that. Okay? Get the information onto the paper so you can guide yourself later on. Help future you think. Okay? Questions about that one? Good, because I just erased it all. Next one. Where do we start? Bromine. Why bromine? It's not hydrogen or oxygen. Cool, I'm just checking. Okay, how many bromines do we have? 4. We've got the 2 and that 2. How many bromines on the right-hand side? 4. How many hydrogens do we have? 4 and 4. Cool. What does that mean? It's balanced. Is that our answer? No, it's not right. What's wrong? Step number 7 was the smallest whole number coefficients. What can we do? Divide everything by 2. Your answer is actually H2 plus Br2 goes to 2HBr. Okay? I had to force this balancing to get this issue to show up. I have a feeling if you go through and follow the rules with standard balancing that we've talked about, you won't run into this issue. Okay? Usually a mistake was made somewhere along the line of balancing to get to the point where you have to then go through and divide by a number. Okay? Questions on that one?
So that might be on the test.
Probably not, because I would have to force balance it, and if I have to force balance it, it starts to give away the answer. Okay. I'm going to go ahead and pause the video. And so we go ahead and start. Okay. You'll notice with all of my symbols, I haven't specified charges. Why do I not specify the charges? Probably not a good thing to do. It's ultimately just being lazy. Okay. I'm not worried about the charges because I don't need to balance the charges, at least at this stage. Okay. If I had to worry about balancing the charges, then I'd absolutely need to watch out for that. Where the charges that are going to come into play is looking at balancing each of the formulas. So remember, before we officially start, we should be checking to make sure each of these formulas is correct. Okay? I'll go ahead and tell you right now, yes, they are all correct. You should verify and make sure you agree with that statement. Okay? Starting with aluminum. How many aluminums do we have on our right-left reactant side? How many aluminums do we have on the product side? We only have 1. Why does the 3 not translate all the way through? The subscript only applies to what's directly in front of it. What's directly in front of it is the parentheses. So everything within those parentheses count. Aluminum's not within it, it's only 1. Okay? Just 3 equal 1, 2 equal 1, sorry. No, what do we have to do? 2 in front, so our 1 becomes a 2. Move to the next atom or molecule. Which one do you want to start with now? Okay, let's take a look at SO4. How many SO4s do we have as a reactant? How many SO4s do we have as a product? 1. How do we make 1 equal to 3? 3 in front. We can move to barium. How many bariums do we have on the reactant side? 1. Why is it not 2? Same issue. The 2 only applies to what's directly in front within the parentheses. Product side, how many bariums do we have? Why do we have 3? The 3 in front applies to it. Okay, 3 equal 1? Nope, what do we have to do? We have to put a 3 in front of our barium to make sure that gets up to 3. How many nitrates do we have on the reactant side? 2. Why is it not 6? Isn't 2 times 3 6? The 2 applies to everything within the parentheses. There are not 3 NO3s. Just like we don't say there are 2 L's. Okay? The L is part of aluminum just as much as this 3 is part of the nitrate. Okay? So we don't multiply through there. It is only 2.
But isn't there 6 now? 2 times the 3 in front.
Oh, yeah, sorry.
Okay, yeah.
I was looking, did propagate all the way out. So not 2 times 3 there. So there's 2 from the formula. How many of those formula units do we have? 3. So it's not the 2 times that 3, it's the 2 times, whoops, that's an eraser. What color am I? Blue. It's the 2 times that 3. Which means how many bariums do we have on our reactant side? We actually have 6. Product side. 3 from our formula unit and 2 from there, 6. 6 and 6, does that balance? Yes. What do we do now? Go all the way back and check it. Aluminum, left-hand side. 2, aluminum, right-hand side. 2, barium, left-hand side. What the heck is that number? So 3, barium, right-hand side. 3, sulfate, left-hand side. Sulfate, right-hand side. Nitrate, right-hand side. Nitrate, reactant side. 6. Yes, I'm bouncing back and forth between different sides. Doesn't matter. No, why not? It's balanced. It doesn't matter which side we look at. It's not going to matter. They're the same either direction. All right? What should we do now? Check it again. Cool. I'm not going to check it again. You guys can check it again. What is the sum of the coefficients for the balanced equation? Add them up and we get 9. Remember, we have that implied 1 in front of our first one. Okay? Last equation. Can we balance based on the polyatomic ion of carbonate? Okay, so let's box in our carbonate ion. Can I balance using polyatomic ions? Why not? Look to the product side. Do we have carbonate? Do we have CO3? No. We cannot balance polyatomic ions in the polyatomic ion method if they aren't the same on both sides. Okay? For the same reason that I can't balance hydrogen with an oxygen. Okay? They aren't the same. So we'll go through the individual atoms. Hydrogen, how many on the reactant side? Oops, sorry. Why is hydrogen a problem? Supposed to start with carbon. That was my bad. I'm sorry. Carbon on the right hand, left hand, that side. Carbon on the other side. Hydrogen on the reactant side. Hydrogen on the product side. Oxygen on the reactant side. Oxygen on the product side. Why not 2? I only see 2 next to CO2. We have to count them in each of the individual things. We also have 1 in the water. Okay. What do we do now? Check it. What do you do then? Check it again. What do you do then? Sure, why not? Check it again. Then what do you do? Probably a good idea to sum up the coefficients, and our answer would be 3. We've got 1s in front of each of those. Okay. Questions about balancing? Okay. What we're going to do is we will keep coming back to balancing equations, but we're going to come back to them as we talk about chemical reactions. So one of the things that you will be responsible for is predicting products in certain types of reactions. Those certain types are really just going to, come back here, are really just going to be in the last 3. Okay? I expect you to be able to predict products in single replacement, double replacement, and neutralization reactions. In the combination and decompositions, as far as the lecture goes, I might push you to try and predict those products, but I would never ask you on an exam to predict those products. Okay? So, the idea behind this slide is to overall summarize each of the general formats between these. When we look at a combination reaction, what are we doing? We take two things and we make them one. How did we do that? We combined them together, hence the combination. If we look at a decomposition reaction, what happens? We take one compound and we break it into the pieces, or we decompose it. Single replacement. What's happening in that single replacement? B starts next to C, and then B is replaced by A when we get to the products. We did only one replacement, so we're looking at a single replacement. What happens in the double replacement reactions? We switch two things, so we're now looking at a double replacement reaction. So the idea is to kind of categorize them as quickly as you can. One of the things that might stand out as kind of, more difficult maybe, is you look at this, what do you think? Looks relatively neat, right? Hopefully. Looks neat?
Yeah.
Okay, yeah, at least one, yeah, that's good enough. Versus that. You should be able to look at each of these equations and tell me what type of reaction occurred. Some of them are easier than others. That first one, what do you think happened? It's a combination. We took two molecules, we smashed them together to make one. Next reaction. Same thing. Took two things and made them one thing. Notice that your numbers may change. The numbers are irrelevant. We aren't concerned about the coefficients. We aren't concerned about the subscripts. What we're concerned about is the bulk changes as we move through this. Last one. Last one. That one, the third one is the hardest in my opinion, that's why I'm skipping. Last one, we start with one thing and we turn it into two things. Decomposition. Okay? So you can start to see how we can identify these things by looking at kind of the larger picture instead of just looking at individual atoms. What happens with the third one, right in the middle? Okay, the double one. If we take a look at aluminum and barium, what happens when we look at them in the products? They swapped spots. Okay? Both of them swap spots, so we're looking at a double replacement. Okay? So the trick is to be able to look for these patterns and try and process them accordingly. One of the other things you'll notice is I did color code this. Blue represents the cation, red represents the anion. The single replacements, we can actually do a different type of single replacement reaction where we're not looking at a cation being replaced. Okay? Fairly rare, we don't see them as often. They come with halogens if we replace the anions. Okay? What we're looking at doing is always keeping the cation first. Why do we always list the cation first? Because IUPAC said that's the way you do it. Okay? So we always start our formulas with the cation, we end them with the anion. So I went through and color matched these in each case to show that swapping back and forth. The last one that can help us out is a neutralization reaction. You'll notice I removed some colors and I've added some things that are permanent fixtures. Okay? Neutralization reactions are more commonly known as acid-base reactions. What is the definition of an acid? Dissolved in water and has hydrogen. Okay? We removed the phase information, which makes this a little bit more difficult, but what can you tell me about that first species? I guess I shouldn't point to it. It's color on it. What does that first species have? Hydrogen, and that hydrogen's in front. What are we looking at? An acid. Oh, that's interesting. Acid begins with A. Look at that. Would have thought I thought about it. What's the next one? Next one has hydroxide as an ion. What do acids react with? It's a stretch, I'm just curious. Bases. What do bases begin with? Holy crap. It's like I really thought about it. Okay? What we're looking at is reacting an acid with a base. What happens in most of our acid-base reactions? The hydrogen combines with our OH to make HOH, also known as water, H2O. One of the other results is that we now make this compound, Ba, which in all cases will come out to be a salt, a metal and a nonmetal. Okay? So the idea is that we want to be able to predict these individual changes, classify our reactions, and try and propagate through. Okay? So we're going to look at 2 example reactions with this, and then we're going to look at one more with a different type. So 3 different types for this type of reaction. The reaction of a metal with oxygen, non-metal with oxygen, and a metal with a non-metal. Okay? These ones I sort of expect you to predict when we have metals and non-metals. Okay? Why would I expect you to predict metals and non-metals? You should know the charges on your metals and non-metals, which means you know how to make those compounds. Okay? So, magnesium metal reacts with oxygen gas to produce. Start it off. That's the end it off. We'll come back to that. Magnesium metal, what's the phase? Solid. Do we need multiple magnesium? Oh, that was a bad idea to do it that way. Just 1 magnesium. How do we know it's not 2? It's not one of those 7 that we were told to memorize. Plus oxygen gas. Would that be correct? It has to be O2 because diatomic. That is going to produce what? Magnesium oxide. What's the charge on a magnesium ion? Charge on an oxide ion? -2. Is our formula balanced? +2 minus 2 equals 0. Our formula is balanced. I didn't ask about the equation yet. Magnesium oxide is now a correct formula. We need to know that formula is correct before we start to balance the equation. Otherwise, we could get things wrong. Okay? Would I expect you to know the phase? Heck no. But I'll tell you it now. It's a solid. Okay? Is our formula balanced? Not balanced. What do we need to do? We need 2 magnesium oxides. Okay? Yeah, I did that right.
Yeah, but then just.
Okay, let's break it down. Since we're seeing some puzzled looks, I'm okay with that.
I'm thinking you just threw the product out of balance by doing that.
Magnesium, how many magnesiums do we have on the reactant side? How many magnesiums do we have on the product side? Right now we have just 1. Remember I erased that too. How many oxygens do we have on the reactant side? How many oxygens do we have on the product side? 1. How do we fix that?
2, you got to put 2 there, yeah?
But then what happens? Now we go back and check magnesium. We now have 2 magnesiums. How do we fix that?
Put 2 on your side.
2 on the other side.
Now you got it.
We did not affect our formula by putting the 2 in front. Why? Because in front it multiplies everything after it. The formula ratio stays exactly the same. Okay? What type of reaction did we just perform? Combination reaction. Ta-da! Okay? We'll pick up there. I was hoping to do a couple more, but I won't get through it. Okay? So there's 2 more examples of combination reactions. We'll do 1 more on Tuesday, and then we'll start moving through the other reactions.